Good afternoon, ladies and gentlemen. Welcome to the new seminar of MetaMAT. So today it's my pleasure to introduce Professor Jean-François Semblat from ENSTA Paris. Jean-François is an expert in modeling approaches and in homogenizations. He's focusing a lot of on metamaterials and metacities. And today he's giving a talk on cloaking of body and surface seismic waves. So Jean-François, I give you the...
Okay, thank you very much. Good afternoon, everyone. Thank you. First, I would like to thank the MetaMAT people for inviting me to give this talk. As already said, this talk deals with MetaSurfaces and MetaBuildings in megacities, and I will focus on the cloaking of body as well as surface seismic waves. So due to earthquakes, seismic waves propagate into the earth, but we may consider either the resonance of the entire planet, the resonance of structures, either geological structures or civil engineering structures. For the vibration of the earth, the resonant frequencies will be of the order of millihertz. But we also have, in many cases, to consider nonlinearities. And for instance, along fault planes, we have to consider permanent slips due to the stress release into the earth, as shown here on this plot for the so-called Tohoku earthquake in Japan in 2011, which struck the Fukushima power plant. And as it is shown on this picture in the red areas, the slip may be as large as 70 meters, not 17, but 70 meters at depth in the earth structure. So it is a huge permanent deformation of the earth crust. So we have to deal with such resonance phenomenon, wave propagation, seismic wave propagation phenomena, and also very strong nonlinearities in many cases. But waves may be used to characterize the earth structure as well as the structure of other planets, such as the structure of planet Mars, as shown here on this plot. As you can see on the right-hand side, we have a seismic recording on the Earth. We have a seismic recording here on planet Earth, on planet Mars. It was performed through the SEIS instrument sent at the surface of Mars in the framework of the IMSIA mission. And as you can see here at the bottom, we have a recording at the surface of the moon. So it is possible by processing such signals to identify the structure of the planets. And in the case of this recent recording on planet Earth, it gives a new insight on the structure of the red planet. And it was a kind of revolution to process such signals, and we have a very new results dealing with the structure of the red planet. At the surface of the Earth, and especially in the big cities, in megacities, as you can see on this video, seismic waves may shake the buildings in cities. And as you can see, even very large buildings may be shaken by the seismic excitation. And for very tall buildings, the period of the shaking will be very large. We may consider a very long period for very tall and very flexible buildings. as you can see here, in the case of Tokyo in Japan. So this is a video taken during the Fukushima earthquake in 2011. And as you can see here, we have an out-of-phase motion, a rightward motion of the left building, when we have a leftward motion of the right building. So it is very important in large cities to investigate the effect of seismic waves and of the dynamic response of the buildings. So the outline of this talk, first of all, we'll investigate the case of seismic waves and try to discriminate between surface waves and body waves, because both of them are very important in the case of earthquakes. We'll also consider in the second part the influence of the buildings at the free surface as a kind of meta-surface in very big, larger cities, such as megacities. And then in the final part, we'll consider so-called meta-buildings, that is, buildings with additional internal variables, kinematic variables, inside or around the building, and changing the interaction, the dynamic interaction with the environment, with the soil and the seismic waves. And then finally, we'll talk about mainly some perspectives dealing with the pore fluids. So first of all, in the case of earthquakes, we have to deal with body waves as well as surface waves. And surface waves are very important in the case of earthquakes. We start with the source of the earthquake, the seismic source. And we are mainly interested in the radiation process of seismic waves. And to do so, we have very simple models, such as couples of forces, as shown in red or in blue on this schematic. And we may define from this couple of forces, we may define the so-called seismic moment tensor. And this tensor allow us to define the so-called moment magnitude, which is proportional to S, which is the surface of the slip along the fault, and to delta U bar, which is the average displacement, differential displacement between both sides of the fault. But we may also consider more complex models, for instance, a rectangular fault plane, an elliptical fault plane, or we may even consider very detailed models accounting for the roughness at the interface along the fault. If we consider the seismic waves propagating in the Earth structure, and especially in the Earth crust, we may observe the seismic motion at the free surface. We may install seismometers, as shown here. In blue, we have a seismogram recorded in the city of Grenoble in the French Alps, as you can see here, and the acceleration is very small in this area, which is mainly a bedrock area, a very stiff medium. But if we compare with the observation at the red triangle, that is the seismological stations located in the alluvial basin, that is on soft soils, as you can see here, the amplitude of the acceleration is much, much larger. It is due to the amplification of the seismic motion due to the velocity contrast between the various soil layers. We may even compare the seismic motion at the free surface. In red, we have the three acceleration components recorded at the free surface of the alluvial basin. We may compare the motion at the free surface to the motion recorded at 500 meters depth. Here in blue, we have the three components, the three signals recorded at depth at 500 meters. And as you can see here, the seismic motion at depth in blue is much, much less than the seismic motion at the free surface due to the amplification of the seismic motion during the propagation in the various geological layers. So as you can see, this amplification process is very strong and is very important. So it is due to the velocity contrast. It amplifies the body waves, but it is also due to the generation of surface waves, as we will see later on. So how is it possible to model seismic waves propagating in complex geological structures? We may consider the finite element, the boundary element, either the spectral element method. We may consider 1D models. In this case, we have 1D propagation with the 3 components of the motion, that is, all the components of the stress tensor. We may also consider 2D or 3D models, but if we work with the finite element method, we also have to account for absorbing boundary condition or absorbing layers to avoid spurious reflections at the boundaries of the finite element model. We may, for instance, consider the perfectly matched layer method or the Colgate absorbing layer method, the so-called CAM method, or it is also possible to couple various methods such as the finite element method and the boundary element method, for instance, to account for the wave radiation at infinity. This is the main purpose of such coupling strategies. Then, if we perform numerical simulations, in the case of the Volvi European test site, the Volvi alluvial basin, as you can see here, we performed simulations in the frequency domain at various frequencies. And this number A is the amplification ratio when comparing the amplitude in the red area to the amplitude in the green area. It means that in this case, the amplification is around 10. That is, the amplitude in the red areas is approximately 10 times higher than the amplitude in the green area. And by changing the frequency, we may compute the amplification in the various parts of this alluvial basin, which is approximately 6 kilometers wide and 250 kilometers deep. And we may compute the amplification at various frequencies. And as you can see, when increasing the frequency, we reduce the wavelength and we can identify the areas of large amplification. If we now move for this Volvi basin case to the time domain, as you can see here, we have the geological structure of the basin, and we plotted in the time domain the response at various locations along the basin. And as you can clearly see here, there is a significant generation of Rayleigh waves, that is, of surface waves, due to the variation of the velocity in each layer, but also the variation of the thickness of each geological layers. Due to this lateral heterogeneities, there is a strong surface wave generation process in play, increasing the amplification of the seismic waves a bit more. So is it possible to identify the contribution of these surface waves in the total seismic wave field? In fact, we proposed a time frequency, an efficient time frequency analysis method based on this so-called Stockwell transform, time frequency transform. So we consider the time domain response, the 3 components X, Y, along the 3 components X, Y, Z, and we calculate the Stockwell transform, that is the time frequency transform of this seismic motion. And then we proposed to consider a normalized inner product combining the radial and the shifted vertical components of this signal in the time frequency domain. So with this normalized inner product, the value should be 1 if the radial and the vertical component of the seismic wave are perfectly in phase. And we may define, in fact, a NIP threshold. So we choose to the value of 0.7 to filter out the contribution of the body waves. Then it is possible to come back to the time domain through the inverse Stockwell transform to get the time domain motion due to the surface waves only. So an example of this technique, surface wave identification and extraction technique, is shown here for the Chi-Chi earthquake in Taiwan. So we have a recording along with respect to the 3 direction of space, and we computed the time frequency transform of each signal for each component. On the right hand side, we have the time frequency components, and as you can see here, we have some strong motion for some specific time windows and for specific spectral components. And then calculating the normalized inner product from these time frequency transforms, we may then plot the normalized inner product for this specific seismic motion due to the Chi-Chi earthquake. As you can see here, the red values corresponds to the cases where the radial and vertical component are in phase. That is, it corresponds to the case where the surface waves prevail in the seismic motion. So if we consider a threshold around 0.7, we will filter out all the blue areas corresponding to body waves. Then we may filter out the contribution of the body waves, as you can see here, and we will only keep this part of the signal. And as you can see, it corresponds to larger time values because it corresponds to lower frequency components for surface waves. And then if we move back to the time domain to the inverse Stockwell transform, time frequency transform, we may get the time frequency surface wave motion as shown on this plot. So these are the filtered motion, time frequency filtered motion through the normalized inner product. And we have the extracted retrograde radio wave due to the Chi-Chi earthquake. As you can see here, we have the 3 motion components. And if we plot the radial and the shifted vertical components, extracted components, as we can see here, we have a perfect match, both our signals are perfectly in phase. That is, we get a pure relay wave extracted from the total seismic record. So it is very useful to investigate the amplification of seismic waves and the interaction with surface structures as well, as we will see later on. So we try to apply this technique to an actual case in the city of Rome. We have the geological structure in the case of in the center of Rome. So we have a first geological section here, and we may identify the surface waves generated, especially near the basin edges, as you can see here, and as you can see here. For another profile, this BB prime profile, as you can see, we have a strong surface wave generation here, but we also have, in this intermediate part, we have a kind of a sub-basin here. We also have a strong surface wave generation process in this case. So it is, this technique with a normalized inner product is also efficient in the case of actual geological structures. Then, if we try to model numerically the propagation of seismic waves, as you can see here, we may consider 3D geological structures for which we have the amplification due to the velocity contrast, wave velocity contrast, but also the amplification due due to the surface waves generation, as we can see here, for long durations. So we developed in the recent years fast multiple boundary element methods, allowing us to model surface seismic wave propagating in complex geometries. And some ongoing works deal with half-space Green's functions for the fast multiple boundary element method, weak coupling approaches, and also H matrices approaches. So these are the ongoing researches in this field. I will not detail much more about that. I will just show you some results for various basin geometries to show the influence of the geometry of the basin on the surface wave generation process. So if we consider various aspect ratios for the alluvial basin, at the top we consider narrow basin, that is the radius of the basin is smaller than its depth, and at the bottom we consider wide basin with the radius larger than its depth. For various geometries, that is cosine, ellipsoid, superellipsoid, and as you can see here, for a narrow basin we get the largest amplification in the higher frequency range, whereas for a wide basin we get the largest amplification in the lower frequency range. And it is possible to compare the influence of the geometry, that is the influence of the shape of the basin on its edges. So it changes the surface wave generation process. If we move from surface waves propagating in geological structures to their interaction with buildings at the free surface, we may consider the so-called site-city interaction. The seismic waves propagate in the deep geological structures, and when reaching the free surface, they may interact with buildings, tunnels, bridges, and the interaction with the buildings may lead to very strong interferences, and we'll talk about that in the second part of the seminar. So if we consider very large cities, megacities, as you can see here, we may have areas with very tall buildings, that is, they will move in the long period range because their eigenfrequencies are much lower than the small buildings as shown here. So it is possible to investigate the interaction with a large number of buildings and seismic waves propagating in the Earth crust and in superficial geological layers. So we may, for instance, identify the height of the various buildings in order to somehow define the roughness of the city, the irregularity of the urban configuration, and we may, for instance, get some simplified maps showing the average height of the buildings in the various areas in a given city. So from such maps, we may investigate the so-called site-city interaction, that is, the interaction between the seismic waves amplified in the superficial geological structures and the buildings located vibrating at the free surface. Some preliminary work we've done many years ago, as you can see here, we consider various viable number of buildings at the free surface of an alluvial basin, and as shown here, depending on the density, the urban density, the interaction between the buildings and the site may be small or significant, depending on the fundamental frequency of the alluvial basin and the eigenfrequencies of the individual buildings, but also the eigenfrequency of the whole building network as well. So from these simulations, we were able to determine the perturbations in the seismic wave field due to the influence of the buildings. So we considered the urban seismic wave field minus the free field seismic motion, and we get the perturbations. That is the influence of the buildings, of the site-city interaction. As you can see here, if we consider more or less homogeneous city, as you can see, we have surface wave generation due to the presence of the building, and the surface wave propagate leftward. And as you can see, the interaction is different depending on the depth of the alluvial layer of the alluvial basin at the various locations. So it is a rather complex phenomenon, and we also investigated this phenomenon for non-homogeneous cities. As you can see here on this plot, we consider somehow dense urban area on the left-hand side. As you can see, the interaction is significant, whereas on the right-hand side, the density of buildings is not so large, and the interaction is not so significant. And we still have this leftward propagation due to the influence of the amplification in the deepest part of the basin. More recently, we considered an actual urban configuration in the city of Rome in Italy. So this is the area where large buildings were built in the recent years, and we have a detailed knowledge of the geological structure in this area, and we try to model the various structures at the free surface to investigate the interaction with the geological structures, and especially the superficial alluvial layers in the basin. So these are the detailed finite element models corresponding to the various buildings. We have small buildings, very tall buildings with deep foundations as well. So we try to model the alluvial layers, the geological layers, and the structures at the free surface in a detailed way through the finite element method. And we compare on this plot the response, the free field response, without any building before the construction of the various buildings. We plot the horizontal component. As you can see here, there is clear evidence of surface wave generation in each of these sub-basins. We also plot the vertical components. So if we compare the horizontal and vertical components, we may identify with our time frequency method, identification method, we may identify Rayleigh waves generated at the basin edges. In the central part of the plot, this is a first case with one building only, and as you can see here, between 1,000 and 1,000 meters and 1,200 meters, you can see that the interaction between the building and the seismic waves propagating into the basin is very strong. And on the right-hand side, for the horizontal component as well as the vertical components, you can see that for the very large building in this area, so this is a 120 meters building with a deep foundation, you can see that the interaction, and in fact the cloaking effect is very strong. So these are the results in the time domain. We may also consider similar results in the frequency domain to account for the effect of either surface waves generated at the basin edges for the free field response, or the effect of wave structure of sites or site-city interaction in the central plot or the right-hand side plot. As you can see here in the frequency domain, we still have this very strong interaction in this area, and we may have some lower interaction. For instance, for small buildings, we may have some interaction in the higher frequency range for small buildings, whereas in the lower frequency range, the interaction is not so strong. The difference with the free field case is not so large. We now move to the interpretation in terms of perturbations, seismic perturbations, that is the total urban field minus the free field. In the case there is no building, so that it was named case A on the left-hand side of the previous slides. So as you can see here, for the case with only one building, we can see the perturbations generated for the horizontal component and the vertical component close to the building. We have part of the energy propagating leftward and a small part of the energy propagating rightward, depending on the shape and the structure of each part of the alluvial basin. In the case where we have all this medium building or very large, very tall buildings, as you can see here, the perturbations are significant in the various parts of the basin. And we may identify the perturbations in terms of both horizontal and vertical component for the small buildings, intermediate one, and very tall buildings. So the cloaking effect on both body waves as well as surface wave is very strong, because body waves are supposed to mainly propagate vertically, whereas surface waves mainly propagate horizontally. And the effect is, the cloaking effect is strong on both wave types. More recently, or in the same period, in fact, we also worked with Kim Fan, Agnès Morel on homogenization methods to investigate site-city interaction. So we considered an anisotropic equivalent layer in gray here to investigate the influence of the buildings at the free surface. And we managed to calculate, either get a closed form solution or a numerical simulation from this homogenization model to investigate the influence of a given number of buildings at the free surface of an alluvial layer. So we got very interesting results when compared to the more complex numerical simulations. The homogenization technique is also very interesting, and we have some ongoing researchers in this field. Third part of the seminar today, we move from the global scale, seismic wave propagation in the alluvial basin, to the local scale of buildings, what I call meta-buildings, and we'd like to investigate the influence of the interaction between seismic waves and complex resonators. So we try to see buildings as complex resonators. So if we consider a single building exciting by a seismic shaking, so it is just the eigenmode of the building shown here. As you can see here, the kinematics in this building may be very complicated. So if we want to investigate the response of numerous buildings at the surface of an alluvial basin, it will be complicated to incorporate all the complexity of the kinematics of such building models. So we may try to model the interaction between the soil and the structure, the so-called soil structure interaction, that is the dynamic soil structure interaction due to the seismic excitation, through various simplified methods. We may consider the so-called macroelement method, for which we focus on the nonlinear dynamic behavior near the foundation of the structure, and we may consider the far-field propagation of seismic waves in the linear range. We may also consider an alternative, which is a recent method proposed by colleagues from the University of Nice, which is called the 1DT 3 components approach. It means that we consider 1D propagation in this T-shaped finite element model. As you can see here, we have the vertical bar of the T, and we have the hat of the T in this area. And in this approach, we consider 1D propagation with the 3 components of the seismic motion, and the dynamic interaction close to the free surface is considered in the 3D configuration. So we may account for the 3D dynamic interactions between the buildings and the soils, whereas the seismic wave propagation at depth is considered in a 1D model, but with the 3 components of the seismic motion. So what about the buildings and their dynamic response? We may consider, if we consider an actual building, it is a complex structure. It may be very tall. We may have many degrees of freedom and dynamic interaction between the foundation, the soil, and the structure. So we may consider complex 3D models, but at the scale of an entire alluvial basin, they may be very complicated to handle. We may consider 2D models, for instance, or very simple 1D model. Such models are oversimplified, so it is not a good alternative. But as you can see on this plot, buildings may very often be considered as periodic discrete media. So if we consider a periodic discrete media, we may think about some homogenization approach to combine the global and the local kinematics in the building and through the interaction with the environment. So we tried to model such buildings through a 1D homogenized finite element model, considering global kinematic variables, U and alpha, as shown here, whereas at the local scale, we may have, for instance, some inner banding characterized by inner kinematic variables, internal kinematic variables, theta in this case. And alpha will be the global rotation at the global scale. So we try to develop such an enriched finite element model considering the periodicity of the building and this global kinematic variables U, capital U, and alpha. And we'll try to investigate the dynamic response, the eigenmodes first, and the dynamic response of such homogenized model. So we first start with the theoretical description of such a building model. So we may have various kinematics in such a periodic building model. We may consider the shear of the building. On the right-hand side, the global bending of the building, but we may also consider the inner bending, for which we may have to come back at the local scale to investigate the internal rotation within the building. For such a case, we may consider a sandwich beam with each of these kinematic mechanisms. So we have the shear mechanism, global bending mechanism, and inner bending mechanism in purple. So this will make the difference with a classical beam dynamic model. This is the contribution of inner banding. So we may write the constitutive law for this homogenized beam model. We have the shear force, which will be related to the derivative of the transverse displacement, but we also have a contribution of the global rotation, alpha. We'll consider the moment due to inner banding and the classical way to consider the moment of global bending. Then we may write the equilibrium equation. So we have the classical equation relating the global bending moment derivative to the opposite of the shear force. And as you can see here, we have to combine the shear force with the inner bending moment derivative to account for this equilibrium equation at the global scale. At the intermediate or on local scale, we may compare the stiffness due to shear and global bending to the stiffness due to inner bending. And at the local scale, we have to account for the derivative of the transverse displacement, the global rotation alpha, but also the local rotation inside each building structural cell, the internal rotation, local rotation denoted theta. So finally, we get a more complex sixth order differential equation accounting for these three kinematics: shear in light blue, global bending in red or brown, and inner bending in purple. So we may solve this equation, try to find the closed form solution for this equation. And in this recent work with my PhD student, Carolina Franco, we try to develop finite element formulation, enriched finite element formulation to describe such internal inner bending phenomena in structural dynamics. So what is the starting point for this work? So we consider the global scale with the transverse displacement, capital U. We consider the global rotation, alpha n at level n. And we may make the link with the local scale, with the local rotation theta. From this description at the global scale on the left-hand side of the schematic, we considered two transverse displacements and their derivatives U2, U4 at the element nodes. And we also considered the rotations, the global rotations in the element. So in total, we have 7 degrees of freedom for our enriched finite element accounting for inner bending. So we propose cubic Hermite interpolation functions for the U1, U2, U3, U4 degrees of freedom, and the classical Lagrange interpolation functions for the global rotations. By writing the weak formulation of the problem, we managed to identify the 7x7 a bit complicated stiffness matrix accounting for the shear mechanism, the global bending mechanism, and the inner bending mechanism. So it was published recently in the journal Computers and Structures. And we finally get the matrix system as follows. So we have this block stiffness matrix here with respect to the displacement and displacement derivatives degrees of freedom, and the global rotation degrees of freedom. We considered a condensed mass matrix only involving the inertial effects for the translational degrees of freedom. And on the right-hand side, we have the generalized forces or the seismic excitation in terms of inertial forces due to the acceleration of the soil. So we try to validate this model by considering a 3D structure shown here. So we have the vertical description of the structure. It is 30 meters height, and 20 meters large. And we also have the top view of the structure. So as you can see here, it is a periodic structure. And we try to compare various approaches. The closed form solution from the equivalent beam model through the homogenization method on the theoretical side. We also consider a detailed finite element model of this type. We detail all the beams and columns of the structure, a detailed 3D finite element model. We considered our enriched finite element model, so-called FM-BEM, that is homogenized beam finite element model. And we also compared to a Timoshenko finite element beam model. So we compared these 4 different approaches, and we tried to mainly focus on our enriched homogenized beam finite element model. So we will first consider the eigenmodes of the structure, the 3D building. Our homogenized beam finite element model is plotted in gray here, and as you can see, there is a very good agreement with the equivalent beam model, that is the theoretical solution, and the detailed finite element model, that is, they corresponds to the diamond symbols and the squares here. And you can see that for the first mode, the second mode, and the third mode of the building, the match is pretty good. Whereas for the Timoshenko finite element model, as you can see here, either for the first, the second, or the third mode, the discrepancy is quite large. So the influence of the inner banding kinematics cannot be catched by the Timoshenko finite element model. So our enriched finite element model is pretty good to catch the inner banding effect, the effect of the inner banding kinematics. Finally, we try to compute the seismic response of the structure. So with the homogenized beam finite element model. So this is the ground acceleration, the seismic excitation applied to the structure. And we compared the detailed finite element model in gray to our enriched homogenized beam finite element model in black. And as you can see, the match when considering the top roof displacement with respect to time, the match is pretty good. So our enriched finite element model, homogenized beam finite element model, is, I think, a good tool to perform enriched simulations by combining several of these structural models to, for instance, a complex geological basin. So we may now move to the strategy and the perspective for future works. First of all, we may consider we have an ongoing research project called Modulate on the interaction between surface waves and long period structures. If we consider, for instance, for the Shishi earthquake, if we consider surface waves extracted from the total seismic wave field, we may investigate the response of structures. So we may, for instance, consider our homogenized beam finite element model to account for the effect of surface waves on the response of such structures, tall structures involving, for instance, inner bending mechanisms. So if we calculate the response of such a structure, tall structure, here is the comparison of the response of the structure in terms of rocking for Rayleigh wave excitation or for body waves excitation only. So this is the response of the same structure to only Rayleigh waves excitation and only body waves excitation, knowing that the total response in terms of rocking is this one on the right-hand side, and we have a specific contribution in the response due to the Rayleigh wave excitation and a specific contribution due to the body wave excitation. So if we try to investigate large-scale interactions at the scale of an entire city, the contribution of Rayleigh waves and body waves in terms of shaking or rocking on tall structures may be very important to investigate in order to identify the cloaking effect for both wave types. Second important topic is the influence of pore fluids. I did not mention any influence or presence of pore fluids in this talk, but we have two ongoing projects on this topic. The first one is the French national project called ISOLATE, for which we try to reduce the influence of the pore pressure, the pore fluid pressure in the soil using bacteria. So I'm not talk much about that, but it is a very original way to reduce pore pressure increase during the seismic shaking. And there's also the ERC European project CoQuake, for which we try with the colleagues from the POEMS lab in the field of applied math, and from École Centrale de Nantes in the city of Nantes, to use fluid injection to try to control earthquakes. I will just show you what may be the influence of pore fluids during a seismic excitation. This movie was taken during the 2011 earthquake, Tohoku earthquake, which struck the Fukushima power plant. It was taken in the center of Tokyo, that is 250 kilometers away from the epicenter. And as you can see here, due to the increase of the pore pressure in the soil, we may have such phenomena that are called, this is called liquefaction phenomenon. It is due to the increase of the pore pressure during the loading, unloading process into the soil during the seismic wave propagation. And you will see all this water comes from the soil is due to the pore pressure increase and the ejection of water and sand grains at the free surface due to the pore pressure increase. So as you can see, the motion is very slow because we only have low frequency components of the seismic excitation far away from the epicenter in the city of Tokyo. And you can see here the geysers due to the ejection of water and sand grains. And this phenomenon called liquefaction. So we also work on liquefaction due true seismic shaking, but it is a bit complicated to analyze such a phenomenon at the scale of an entire city and an entire basin. So, thank you very much for your attention.
Thank you very much, Jean-François, for the nice talk. Now we have time for questions. So just please, you can raise your hand or just go ahead with the questions. And if you don't have a microphone, you can ask questions in the chat directly.